Okay, we had Monday off, so it seems like it's been a long time since we've been in the same room together. Thanks for playing. Let's get started. We got a good stuff on our agenda tonight. Let's take a look at what we're going to be doing. I just want my blue pen. Thought I had every color. Gotta have all 4 colors or I'm not happy. Here we go. And these notes, I'm going to update the notes that I posted. You know, I do post the notes if there's a class before, but I'm going to update them with sort of a slightly better version. But it's all the same content. Look, today we're going to talk about, well, a new kind of statement operator called the conditional operator. So in section 2.2, we're going to talk about conditional statements. And I'm just going to double check my video settings and just make sure that we are in high def. And yes, we are. Okay, great. So conditional. What?
I just had a quick question before we started.
Okay.
Yeah, it had to do with the special homework that we had. I was just kind of confused a little bit on the scanning part. I had submitted it, but I was just trying to make sure that I had did it correctly.
Well, Hossein, you know, when you filled in the online form for eligibility in this class, one of the things that you had to check was that you know how to scan and create a PDF.
No, I did it, but I was just trying to double check with you because I never did it before. So
okay, well, the time to ask me that would be to send me an email so that I can do that not during class. Is that okay?
Okay.
I'll be taking a look at them.
All right, thank you.
You're welcome. Let's start it again. Yeah, if you have, you know, questions, specific questions about your work, folks, you can always bring that to an office hour or an email. Like I can't stop class right now and check, you know, what you turned in. So folks, we're going to be looking at what are called conditional statements, and we've got a little bit of glare. Let's see if I can reduce that. Conditional statements, which are also known as implications or if-then statements. Okay, these all mean the same thing. It's a bunch of different ways to say the same kind of statement. Then we're going to talk about what are called the sister conditionals. And you'll see what I mean when we do that. And then we're going to up the ante and talk about biconditionals. Okay, so that's section 2.2. And then it is a natural segue into section 2.3 on arguments, because it turns out arguments are conditional statements. Yeah, focus is a little better there. And an argument, I'll just write it here just for your reference, but we'll understand what this means a little bit better, would be a bunch of atomic statements ANDed together with this new conditional operator pointing to a conclusion. And like I said, by the time we get to this, you're going to understand what that means a lot better. And then we're going to look at an algorithm for argument validity. In other words, we're going to ask ourselves this question: is this argument valid? And this is a decision algorithm. Okay. Everybody in here is computer science and knows what an algorithm is, right? An algorithm is just a sequence of steps or a procedure to perform some task. And in the case of determining argument validity, the task would be to decide if a particular argument is valid. So section 2.2, conditional statements. Let's take a look at what I mean when I say a conditional statement. So the notation goes like this. We have a P and then an arrow toward Q. P and Q represent any kind of statements. And we call P the hypothesis, and Q is called the conclusion. And the way that we read this, there are a couple of different ways to read this. You can read it as if P, then Q, or you can read it P implies Q. Either one is perfectly fine. All right, so we'd like to understand this new operator. In other words, we'd like to know, when is this new compound statement true, or when is it false? Okay. Sorry. So let's make a truth table. We know that a truth table is one of our tools for understanding what a rule looks like for a particular kind of operated statement. So here's our truth table. We'll have a P and a Q and a P arrow Q, or P implies Q. And this is just going to be our basic kind of 4-row truth table. Under P, of course, we're going to write true, true, false, false. And under Q, as usual, we'll write true, false, true, false. And when we set up a 4-row truth table, we always set it up in this canonical way. All right, I'm going to actually write the rule with words, and then you can help me fill in this column. The rule for when P implies Q, or if P then Q, is true and when it's false is like this. It's kind of easier to talk about when it's false. P implies Q fails only when P is true and Q is false. That's the only time it fails. Otherwise, it's going to be true. So when we look at the truth table, which row are we going to put the false in, folks?
The second row?
Yeah, because this is the row, good, where P is true and Q is false. This is the only time that if P then Q fails, folks. And listen, the intuition behind if P then Q. The intuition is this. If P then Q only tells us what should happen if P is actually true. It doesn't speak to what should or shouldn't happen if P is false. It only says, hey, if P is true, then Q needs to be true as well. In other words, if P is true, then Q should follow. Like when we just say P, we're saying P is true. When we state Q, we're really saying Q is true. So if P then Q only says what should happen if P is true. P is the condition. It's the hypothesis. If P is true, then Q better follow. So the only time it would fail would be if P is true and Q doesn't follow. In other words, Q is false. So we have true everywhere else here. And this is not intuitive for students. And I'll tell you why. Let's look at these last 2 rows. The last 2 rows in this truth table, look, we've got false implies true is true and false implies false is true. And that's kind of against our intuition, isn't it? It's against our intuition because intuitively, you know, if we've got a couple of falses, we can't really imagine that that yields a true. But for the if-then operator, it sure does. For these 3rd and 4th rows, we say that if P then Q is true by false hypothesis. All right. Now, I just want to talk you through some of the equivalent ways to say if P then Q. There are lots of ways to say P implies Q. Hold on, my cat is going crazy. Let me let that kitty in. Good grief, Winnie. You were supposed to come in an hour ago. What are you doing? Come on. You're a nuisance. No, you're a nuisance. Come up. Shut up. Sorry about that. The joys of working from home. So there are lots of ways to say if P then Q, folks. Oh, and listen, if you look on the reading page, which has been updated, you'll see a pointer in the Good Stuff column to a new document in the Good Stuff folder in Blackboard, and that new document is called If P then Q. And that document is like a ready reference about if P then Q. It'll tell you everything you ever wanted to know about if P then Q and more than you ever wanted to know. So you can refer to that. But here are a few different ways that we can say if P then Q differently. We can say Q if P. That means if P then Q. Q will be true if P is true. That's the way to interpret that. Okay. Another way to say if P then Q is P only if Q. P will be true only if Q follows. That's the way to understand that. These all mean if P then Q. Not Q implies not P. Now, it's hard to believe that that means the same thing as if P then Q, but we're going to actually explore this at some length in just a few minutes, so just trust me on this. P is sufficient for Q. So the way to understand this, and I don't want you to try to memorize these, I want you to try to talk yourself through these, is P being true is sufficient to make Q true or to force Q to be true. In other words, if P is true, then Q better follow. P being true is sufficient for Q to be true as well. Another way to say it is Q is necessary for P. Why does that make sense? Let's think about it. Q must necessarily be true for P to have been true. Because if P is true, then Q's got to follow. So Q must necessarily be true for P to have been true. Does that make sense? So we got to kind of, be fluid with our English. And here's a non-intuitive way to understand it. Q or not P. This means the same thing as if P then Q. Let me see if I can explain it. And we're going to visit this again in a moment too. We have statements that are always true. Does anybody remember what such a statement is called? We have a word for it. A statement that's always true.
Is it totality?
That's right, a tautology. Nice. Here's a very simple tautology. It's kind of like one of the first examples of a tautology you might see. P or not P. That is always true. P or not P. Because, if P is true, then P or not P is true because P is true. If P is false, that makes not P true. So P or not P is still true. So if you think about P or not P, and we're trying to understand P implies Q, well, it's either P or not P. But since P forces Q, then instead of the P, we can put Q. So it's Q or not P instead of P or not P. And we're going to look at truth tables to convince ourselves that this actually makes sense. All right. Let's look at an example. Let's give ourselves a key and let's let P be the statement, it is a rose. And Q be the statement, it is a flower. Okay, so that's going to be our key. We're going to write the informal, that means ordinary English, of course, statement for each formal statement. And we're just going to explore some of these. Okay. A. P implies Q. B. Q implies P. C. Not Q implies not P. Let's just start with these. All right. All right. So for A, P is it is a rose. Q is it is a flower. So if P then Q is if it is a rose, then it is a flower. True or false? If it is a rose, then it is a flower.
True.
Sure. If what we're looking at is a rose, it's definitely a flower. So this is a true statement. Now there's a reason why I'm bothering to go with the truth values. I want to make a point here. B, if Q, then P. We've just switched the P with the Q. B is actually called the converse, okay? And don't worry, we're going to write that down in a minute. So let's write B informally. If it is a flower, then it is a rose. True or false? If it is a flower, then it is a rose.
False.
That's right. Why is it false? Can you give me what's called a counter example?
Because not every flower is a rose.
That's right. Not every flower is a rose, right? You know? So Nick, what's your favorite flower that's not a rose?
Dandelion.
There we go. So just because it's a rose, a flower doesn't make it a rose. Okay. How about C? Anybody?
Is it if it is not a flower, then it is not a rose?
If it's
That's right. And you can say it is, or you can say it's. If it's not a flower, then it's not a rose. True or false?
True.
Sure. And I'm trying to make a point here. The original, if P then Q, and the converse, if Q then P, don't necessarily have the same truth value. Here they do not. They have opposite truth values. There's no way that if P then Q and if Q then P could be logically equivalent, because we have an example right here where one is true and one is false. But check out if not Q, then not P. I want you to think about that and think about the original, if P then Q. Do you see that they're really saying the same thing? If it's a rose, then it's a flower. Means the same thing as, hey, if it's not a flower, then it can't be a rose. Because if it's a rose, then it is a flower. So if it's not a flower, it can't be a rose. See what I mean? These actually mean the same thing. A and C are actually going to be logically equivalent, always. And we're going to be looking at these different versions of related conditionals. Let's do that now. So I call these the sister conditionals. And it's after some Indian folklore about the sisters that you plant together, squash, beans, and corn, and they grow together perfectly. And so when we have an original conditional, if P then Q, let's just call that the original. There are three sister conditionals that are associated with if P then Q. One of them is if Q then P. You just switch the hypothesis and the conclusion. This is called the converse. And we've just seen an example that shows that they could have opposite truth values. It is possible that they could be both true, but in this example, it shows they certainly don't always have to both have the same truth value. If not Q, then not P. This has a name as well. It's called the contrapositive. The contrapositive, it turns out, is the one that you get by doing everything you could to change the original. Notice we switched the positions of the P and the Q, right? And we negated them both. So you really couldn't do much more to change if P then Q than to create what looks like this, not Q, then not P. But the irony of it is doing that actually creates a statement form that is logically equivalent. There's one more. If not P, then not Q. Notice on these, for all of them, either you've got just the statement, atomic P, atomic Q on either side of the arrow, or you have both of the hypothesis and conclusion negated. None of these would have one of these negated and one not. And so that makes it a little bit easier to realize, hey, there's only 4 different ways to change that up. The original, the converse, the contrapositive, and the inverse. So there's something I want you to do later, and I hope that everybody understands that when I say do later, this is a really important thing to actually do, because would be like a good quiz or test question. Complete this truth table, TT for truth table, and then answer this question. Which of the sisters, I'll just put sisters in quotes, are logically equivalent to which? Okay, so I'm going to skip a couple of lines, at least one line here, so that we can see what's going on. So P, Q, not P, not Q, P implies Q, Q implies P, not Q implies not P, and not P implies not Q. Okay? We're going to complete that truth table. We are not going to do it all now. You're going to do it later, but I'll get you started because I want to make sure that everybody understands how this rule works for the if-then operator. So under P, of course, we have true, true, false, false. And under Q, we have true, false, true, false. I just want to point out to everybody, we always put our variables in alphabetical order. So of course, P goes first, then Q as usual. Let's move right over to, I'll let you fill out not P and not Q. You know how to flip the bit. So under P implies Q, we learned tonight that it's only false in row 2. And it's true everywhere else because an implication only fails if the hypothesis, which is the part on the left of the arrow, the hypothesis is true, and the conclusion, which is what the arrow points to, is false. It's the only time that that implication would fail. So let's look at the converse. Let's look at this column for the converse. In which row should we put the false for the converse? Anybody?
3.
Third one.
That's right, because that's the row where the hypothesis, which is now Q, is true, and the conclusion, which is now P, is false. And it's true everywhere else. In which rows is the converse true by false hypothesis? In which rows is the converse, if Q then P, true by false hypothesis? Anybody?
The fourth one.
It's certainly true by false hypothesis in the 4th row because the hypothesis is Q and the hypothesis is false in row 4. Good. There's another row.
Second one.
That's right, in the 2nd one. Now I'm good. So now that you understand a little more generally how to fill out the truth table for an if-then statement, I'll let you finish these, and then you can compare the columns for these 4 conditionals. that are related in this way and figure out which are logically equivalent to which. Okay? Now, whenever we learn an operator that's what we call a binary operator, like the and, or, and now the if-then operator, the next question we should be asking ourselves is, hey, what happens when we negate that new compound statement? We learned De Morgan's laws to negate and or statements. Well, now we need to learn the rule that tells us how to negate a conditional statement. That's what we're going to do next. Negating the conditional. Okay, so here's the rule to know. If we want to negate if P then Q, there is not an operator that is an arrow with a slash through it, unfortunately. We don't have that operator, okay? So what we really have to do is think about what it means to say, hey, P didn't imply Q. And this is what it means. It means P happened, P is true, and Q failed, which means not Q is what is true. P happened and Q didn't follow. This is what the negation of P implies Q looks like. Now, you don't have to believe me. Let's take a look at a truth table and see if it really is right. So here's P, here's Q, here's P implies Q. Now we'll negate P implies Q, okay? So that'll for sure means not P implies Q. We'll look at not Q, and then we'll and P with not Q. And let's just compare the columns for the negation of P implies Q with the column for P and not Q. And let's verify to ourselves, yeah, man, they better look the same. And they're going to. So under P, it's true, true, false, false. Under Q, of course, it's true, false, true, false. And of course, if we had an 8-row situation where we had a P, a Q, and an R, it would be true, 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 false, 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 false under P. Then under Q, it would be true, true, false, false, true, true, false, false. And then under R, it would be true, false, true, false, true, false, true, false. All right, here we go. We know that under P implies Q, we have true, false, true, true, right? Now we can quickly construct the column for not P implies Q by just flipping the bit. So it's false, true, false, false. Everybody with me? Now, let's make the column for not Q. False, true, false, true. We're just flipping the bit. We're just flipping the truth values for Q, right? Good. Finally, let's go ahead now and let's create the column for P and not Q. By the way, do you like this view or would you prefer to see the view where it's multi-speaker? Which one do you like better, this view or this view? Do you like, this is called the speaker view, or we have the multi-speaker view. Does anybody have a strong preference? All right, we'll just play around with it then. Let's try it this way because I can see everybody. P and not Q. Here we go. We're going to and together P and not Q. So true and false. What is that? True ended with false. False. Thank you. Yeah, I saw it in the chat. Great. All right. Row 2. True and true. Thank you. True. Row 3. False and false. That's right. Thanks, Hossein. Row 4. False and true. False again. Thanks, Hussein. All right, so here we go. Check it out. These are logically equivalent because these are identical columns. So it's really important to understand that when we negate an if-then, the result is not another if-then. I'm telling you, about 25% of the folks in here are going to miss a lot of points on the next homework, special homework 2, which is already up, and on test 1. About 25% of you are going to make this mistake. When you negate P implies Q, you're going to tell me that that's some other kind of if-then statement, but it's not. It's an and statement. So here's the really important thing to understand. The negation of an implication, of a conditional, it's also called an implication, is not another implication. It is an and statement. The negation of an if-then is not another if-then. It's an and statement, okay? Super important. All right, let's do a do now. Example 2. We're going to use the same key that we used before, okay? P is going to be, it is a rose. And Q is going to be, it is a flower. And now we're going to write each statement informally. And we're going to practice with the names of these 3 sisters. Okay, so I'm going to put the names up. Here, and I'm going to write the rule that the negation of P implies Q is P and not Q right here so that you can see it, so that you can see everything. Okay. I know it's redundant, but I'm just putting it there so you can see it here in the video. I'd like you to write the contrapositive of P implies Q informally in ordinary English. The inverse of P implies Q, and the negation of P implies Q. Okay, we're going to do that now. And we've already done one of these, but it doesn't hurt to kind of see this from a couple of points of view. The point of view of this problem is a little different than the last one. Here we're learning the names, okay? The contrapositive. If not Q, then not P. So if it is not a flower, then it is not a rose, right? Because not Q would be, it is not a flower. Not P would be, it is not a rose. How about B? What should we write for B? The inverse. Anybody? Nice. If it is not a rose, then it is not a flower. Let's see. And that would be, I'm looking to see who that would be. AS is Stephen. Thank you. If it is not a rose, then it is not a flower. And now let's write the negation. What does the negation look like? It is a rose and it is not a flower. Nicely done. It is a rose and it is not a flower. Okay, so and you're going to get some practice in WebAssign, that's already up. And I caught up with the reading page, and you'll be able to see everything. Listen, here's another do later. Again, look at example 1 and example 2 and the do later from page 2. And again, answer this. Which of the 4 sisters are logically equivalent to which? It matters. Okay, it's just such an important question. I'm asking it 2 different ways tonight. Okay, so we've started playing with the if-then operator. Okay, and you're going to need some more practice to get completely comfortable with it. But now it's time to up the ante. What do I mean? There's something called the biconditional. Oh my goodness. We've gone from the conditional to the biconditional. What could that possibly mean? Well, let's take a look. Here's the notation, folks. It's a new operator. It looks like an arrow pointing to both P and Q. And the way we read it as P if and only if Q. P if and only if Q. It's the way it's read. Let me give you the definition. It's going to mean exactly what it looks like it means. The biconditional statement, that's what we're going to find. We're going to define the biconditional statement, denoted by P with the double arrow Q, means P implies Q and Q turns around and implies P. Just like you think it should. All right. Now, I'm going to chase a little rabbit. We're going to do a little aside here. I just want to talk a little bit about trying to use the book to actually find out information. We now have a bunch of statement operators. We have the not, and, or, the if-then arrow, and now the biconditional. Before we go any further, we need to talk about the order of operations for logical operators. I want you to practice. The reason I'm asking you to do this is I want you to practice getting into the ebook and finding stuff. So I want you to read about the order of operations for what are called logical operators. To learn this, I want you to look for it and see if you can learn this. And I'm going to try to help you, but I want you to practice trying to do a search. Because when you do a search, if you put in order of operations into the search bar, a bunch of stuff is going to come up from chapters that we're not in. The idea is to understand that you're going to be looking for a result that's in section 2.2, because that's the section that we're in, okay? So this is what you're going to learn, that the not operator comes first. Then the and the or operators get evaluated next. This is if there aren't any parentheses to help you out. And then the if then or biconditional operators would get evaluated last. This is the correct order of operations. So when you start poking around to try to find this idea using the search in the ebook, I'll just give you a little bit more information. This appears in section 2.2, just below the truth table that's displayed there for the biconditional. There's a truth table for the if and only if operator, and this will appear right below that in the book. So my question is, can you find this in the ebook? Try to do it, okay? All right, so that's my little commercial about trying to find stuff in the ebook. It's not quite as easy as one would like it to be, okay? So it's good to go ahead and, try to get a little practice. All right, let's get back to the biconditional. Oh, by the way, according to this order of operations, if I put no parentheses here at all, then the and operator would get executed before the if-then arrows. And that would mean the first thing that would happen would be Q anded with Q would happen first. And then these arrows would somehow have to be evaluated afterwards, and that doesn't even make any sense. So here's an example that you could practice on. And you have already seen this in WebAssign, but you may not have really thought about the fact that you were looking at truth tables for expressions that did not involve parentheses. But the way that you got away with it is because in WebAssign, the way it's set up is the truth tables are already set up for you. The columns, that build up to an expression are already labeled for you. So you didn't have to do any thinking to figure out, hey, what am I supposed to do first? The not or the and, or now the arrow? Well, this tells us the and would happen before the arrow, and the not is always tight. It always gets evaluated first. So these two mean the same thing. All right, so now let's go back to P implies Q, if and only if Q, excuse me. Let's go back to P if and only if Q. All right, so listen, P if and only if Q is actually shorthand for the following. It actually means P if Q and P only if Q. So let's look at the definition of P if and only if Q. It's if P then Q and if Q then P. So here's the and operator. Here's the and. What that means is that one of these two expressions in parentheses means P if Q, and the other one has to mean P only if Q. This brings us back to what we started with on page 1. Different ways to say if P then Q. So the and is right here. My question to you is, which of these two, if P then Q or if Q then P, means the same thing as P if Q? And that means the other one, of course, means the same thing as P only if Q. Anybody want to take a stab at it? Which one of these two implications means the same thing as P if Q? It's kind of a mind bender. What goes here? If P then Q or if Q then P? Anybody? P if Q. P must be true if Q is true. Which one of these is that?
Is Q implies P?
It sure is. If Q, then P means P must be true if Q is true. Very nice. And that means P only if Q must be P implies Q. Again, just, I don't want you to memorize these. I want you to try to kind of be able to talk them through. P is true only if Q is true. P is true only if Q follows. If P is true, that can only happen if Q follows. Okay, there's yet another way to say P if and only if Q. There is another way to do it. And it's this. P is necessary and sufficient for Q. Which is shorthand for P is necessary for Q and P is sufficient for Q. It's another way to say it. And listen, I cannot overemphasize the importance of necessary and sufficient conditions in mathematics. When we have two conditions and we say they are necessary and sufficient for one another, it means that they are logically equivalent notions. If you've got one, you're going to get the other. And if you have the other, you're going to get the one. It means that they're saying the same thing, maybe with different tools, maybe with different objects. And that's one of the big things that mathematicians do is you play around in like one world, like maybe in the world of topology, maybe you're playing with manifolds. And then you're playing over here, maybe with vector spaces, and then you make a result over in one world, and then you try to map it over into this world to learn something new about this world that you couldn't prove inside this world, but it is easier to prove over here. We try to map back and forth between different universes of discourse, so to speak. Again, one of these means P arrow Q, and one of these two means Q arrow P. P is necessary for Q. That means P must necessarily follow for Q to have been true. P is sufficient for Q means P is enough to force Q. Okay? Now, how do we evaluate P if and only if Q? Let's take a look at its truth table. Let's see what the rule is. We're going to first evaluate it, and then we're going to figure out if we can write the rule. Like, when is it true and when is it false? All right, here we go. P, Q, P implies Q, Q implies P, and we know if we and those together, that's what it means to say P if and only if Q. You know, it means this by definition. All right, here we go. True, true, false, false, under P, of course. True, false, under Q. Under P implies Q, we've already done that a couple of times. It's true, false, true, true. Under if Q, then P, we've done that a couple of times. It's true, true, false, true. And now we're ready to and these two together. Row one, true or false? P if and only if Q.
True.
Nice, because these are both true. Row two. False and true. False, nice.
False.
Hossein, thank you. Row three.
False.
Good. Row four.
True.
True. So let's see if we can write the rule. What do we see happening here? What do we see happening here? P if and only if Q was true in two situations. When P and Q were both true and again when P and Q were both false. P, if and only if Q, is true exactly when P and Q have the same truth value. I.e., both are true or both are false. Okay? We are ready to segue right into arguments, because arguments are really interesting conditional statements. They are if-then statements. We are now in section 2.3. Here's our definition. An argument is a conditional statement of the form here we go. P1 and P2 and ... and P sub, let's say K, let's say there are K of those, implies Q. All right, so let's talk lingo. These components, and see, this is an if-then, oh, it's a conditional. In this hypothesis, these components are called the premises. P1 and P2 and P sub K, these are called the premises. And this compound conjunction, this big and statement, is, of course, the hypothesis. And here we have the conclusion. And notice the hypothesis is a conjunction of premises. It's a big old fat and statement. Let's talk about what we understand so far about if-then statements. If the hypothesis is false, then we know an if-then statement is true by false hypothesis. If this hypothesis is false, there's nothing we need to do. We don't need to check anything because we know that the if-then is true by false hypothesis. The work happens when the hypothesis is actually true. If the hypothesis is true, we have to check that the conclusion really follows to check whether this if-then is true. So let me ask you this. What does it take for this hypothesis to be true? Thinking about what you understand about conjunctions and statements, what does it take for this hypothesis to hold? Anybody? All true values. That's right. And I've been saying Hussein, but it's not. It's Ronnie Huggins. It's Ronnie, right? Is that you, Ronnie? RH? So sorry, because I saw the H and I'm so sorry. It's Ronnie. Okay, great. All right. Hussein was perfectly willing to take the credit. That's cool. All right. Ronnie's right, man. Think about it. For this big conjunction to be true, each of these premises has to be true, right? So that's actually going to make our life really, really easy. Because when we start executing this decision algorithm to figure out if a particular argument form is what we actually will say valid instead of true, but I'll explain that in a minute. When we're checking that out, we really only have to check when all the premises are actually true, because if any of these premises is false, the hypothesis is false, and the if-then is true by false hypothesis. So before we get into our algorithm for how to check for argument validity, and we're going to define that, I want you to just see what the usual format is for an argument. We don't actually usually write it horizontally, even though, you know, statement forms are generally written horizontally. Arguments are so special, they have their own form. We write them vertically. So we put each premise on its own line. So however many there are, say K of them. So P1, P2, dot, 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 P sub K. And then we draw this symbol, the 3 bowling ball hole symbol. Does anybody know what that symbol actually means? Has anybody ever seen that one before?
Means therefore.
It does. It means therefore. Nice, Eric. So this means therefore, or we can conclude that. And then we put the conclusion Q. Okay. So we line up the premises, one on each line, and then therefore the conclusion. Okay, that's the general normal form that we would write an argument. All right, now let's talk about this decision algorithm. We're doing okay for time. In order to understand the decision algorithm, we have to understand what we're trying to do. We always want to figure out what the truth value of a statement is. It's always the game. Is the statement true or false? Arguments are such special and specific statements that instead of saying they're true or false, we actually use this language. We say they're either valid if they're true or invalid if they're false. Okay? So let's write that down. Valid versus invalid arguments. Or argument forms. You can think about it either way. Here's our definition. An argument, I'll write it horizontally here, P1 and P2 and dot dot and P sub K implies Q is valid. So we're defining what it means to say an argument is valid if the conclusion, which is Q, is always true when all the premises are true, i.e., when the hypothesis is true. So this is sort of a fancy application of the rule for when we determine if an if-then statement is true. Okay? The conclusion must follow if the hypothesis is true. All right, so folks, I'm going to drop a short video. It'll be in the YouTube channel under the playlist Shorts for 263. And I will finish whatever we do not have time to do today in class about this idea of using an algorithm to determine argument validity. But we're doing well on time. So let's take a look at example 1. Again, we're in a new section, so it's section 2.3. So we'll call this example 1. Let's look at this argument form. The first premise is P or Q. Okay, that's premise 1. You don't have to write that, but I'm just doing it for the notes. Second premise, if P, then R. Third premise, if Q, then R. We have 3 premises here. Therefore, R. That's our conclusion. Let's think about this for a minute. Let's think about what this argument is actually saying. We assume the premises are true, okay? So we have P or Q. We also know that if P, then R. We also know if Q, then R. Do you think this is going to be valid to conclude, therefore, we've got R if we have these three premises, just using your intuition? Like, the algorithm is not going to be intuition. It's going to be a very cut and dried way to for sure figure it out. But let's just think it through. We have P or we have Q or both, right? It's the inclusive or. We know P gets us R. We know Q gets us R. Can we conclude, do you think, therefore, that we're going to get R?
Yes.
That's right. If this is going to turn out to be valid. Now, let me talk to you about the decision algorithm. For determining argument validity. Okay, there is an algorithm. I want to give you the steps now. And I want you to also, the document posted in the good stuff folder, and there's a pointer to it in the reading page, and it's a document where I have worked through 2 examples of using this algorithm. All right, so I'm just pointing you to extra materials here. Here we go. The algorithm goes like this. Step 1. First thing that we're going to do, oh, by the way, this is application number 3 of truth tables. We've seen 2 other applications for truth tables. This is our last application or main way we're going to use truth tables, just FYI, is to figure out argument validity. All right, so here's our definition of argument validity. Step 1, make a truth table with a column for each premise and for the conclusion. So that's the step that takes the most time. You build a truth table. So for this example, we would make sure we had a column for P or Q, a column for P implies R, a column for Q implies R, and then a column for R, okay? And you build up to some of these. Some of these can get kind of gnarly. You might have to build up to them. All right, so get your truth table set up with a column for each premise and the conclusion. Step 2, we're going to identify what are called the rows of interest. I'm going to define that for you. These are called the ROI, rows of interest, i.e., the rows in which all the premises are true. Now, why would we need to do that? We want to identify the rows in which all the premises are true. Well, let's go back up and think about our earlier discussion. We only have something to check when the hypothesis of the if-then is actually true. And when the hypothesis is a huge conjunction of premises, it's only true if every single premise is actually true. So the only rows that we have any work to do in are rows where all these premises are true. In other words, the rows where we have a true hypothesis. Because again, if it's a false hypothesis, the if then would be true by false hypothesis. So step 2 is just to figure out which rows have every single premise true. Those are the rows we have to check the conclusion in. And that's step 3. In each row of interest, check the truth value of the conclusion. Okay? Because it's only in those rows that we need to check the conclusion. And then the decision. Step 4 is the actual decision. It's an if, then else. If the conclusion is true in every row of interest, then the argument is valid. My dog is dreaming. Else, the conclusion fails in one or more rows of interest. Rocky, are you dreaming? Else the conclusion fails in at least one row of interest. That's all it takes. All it takes is one bad row to make the argument invalid. And the argument is invalid. Good Lord, I've got a menagerie here. Dog is dreaming, cat is meowing. My goodness. All right, so does it make sense? Does the algorithm make some kind of sense based on what you understand about, what does it take for this if then to be true? All right, so now we do have 5 minutes, so we can get started on executing the algorithm for this particular argument form. All right, let's do that. All right, here we go. Here's P, Q, R. We need P, Q, and R. Oops, you got to be able to see the argument. There it is. P, Q, and R. Step 1, make a truth table with a column for each premise and the conclusion. All right, so here we go. We need a column for P or Q. We need a column for P implies R. We need a column for Q implies R, and I didn't have to really build up to these because I've got enough. And then I'm just going to rewrite the conclusion column R because I like to. By the way, I want to add a little bit of instruction. When you make this truth table with a column for each premise and the conclusion, I'm going to label them as such. Why? I'll tell you why. When we label them, it makes it super easy to see what we're looking at. Here's premise 1, here's premise 2, here's premise 3, and here's the conclusion. By doing that, I'm going to make my life a lot easier when I get to step 2, when I'm trying to identify the rows of interest. When we're trying to do that, we need to see where the premises are. And it's real easy for your eyes to shift around. All right, here we go. Under P, true, 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 true. This is the canonical setup for an 8-row truth table. Then false, 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 false. Under Q, true, true, false, false. So it's first it's 4 and 4, then 2 and 2, true, true, false, false. And then under R, it just alternates. True, false, true, false, true, false, true, false. Okay, so we need to fill in the column for P or Q. It's usually true, right? If one or the other or both P and Q are true, then P or Q will be true. So in row 1 and 2 and 3 and 4 and 5 and 6, at least one of P and Q is true. So P or Q is true in the first 6 rows. But in rows 7 and 8, P and Q are both false. So we have false, false in rows 7 and 8. P implies R. Okay, now we got to just be careful. True implies true is true in row 1. We're looking at P as the hypothesis, R is the conclusion. Row 2, true implies false, false. Row 3, true implies true, true. Row 4, true implies false, false. But look at rows 5, 6, 7, and 8. Look at the hypothesis, P. It's false in rows 5 through 8. So P implies R will be true by false hypothesis in those rows. Super easy. Now Q implies R. Now the hypothesis is Q. In fact, you know what I'm going to do? I'm going to look for when I have false hypothesis. In rows 3 and 4, I have false hypothesis. I know the if then is true. In rows 7 and 8, Q is false. Q implies R will be true by false hypothesis. Now we'll go back and check what actually happens with R for the other rows. In row 1, true implies true is true. Row 2, true implies false is false. In row 5, true implies true is true. And then 6, true implies false is false. And I'm just going to rewrite the conclusion here just because I like to see it on the right, but you don't have to do that. All right, so we have just executed step 1. We have made a truth table with a column for each premise and for the conclusion. Step 2. Now, here we go. We're going to identify the rows of interest, the rows in which all those premises are true. And that's why it's nice that we've labeled these premise columns. So in row 1, see here are the 3 premise columns. True, true, true. Row of interest, yeah. Row 2, is row 2 a row of interest, folks? Are all the premises true in row 2? Nope. Row 3, true, true, true. Yes, it's a row of interest. Row 4, nope. Row 5, row of interest. We're not looking at the conclusion, folks. We're just looking at the premises right now. And then in rows 6 and 7 and 8, at least one of the premises is false. So we have 3 rows of interest. And now we're going to execute step 3. For each row of interest, we're going to check the truth value of the conclusion. So we only have 3 rows to check. We're checking the truth value of the conclusion. The conclusion is R. Oh, it's true in row 1. Oh, it's true in row 2. And it's true, in row 3. And it's true in row 5. That is step 3. We have checked the truth value of the conclusion only in these rows of interest where all the premises are true. And then step 4 is the decision. And we can say, hey, the argument form is valid because the conclusion is true in every row of interest. I can even cite the rows 1, 3, and 5, i.e., in every row of interest in which all premises are true. And that's it. It's a valid argument form because in every row of interest, we got a true conclusion. Question? Well, I am going to drop a short video. Listen, we have an office hour at 8 p.m. tonight. So I'm going to shoot out a little reminder email to all 3 sections that there's an office hour tonight. That will also be recorded if anybody attends, right? And the notes will be posted. So far, I haven't had any attendance in office hours. And then if I have the energy, I'll make this short video tonight to go along with that document that's in the good stuff folder. Otherwise, I'll drop it in the morning. Any questions? So if you have if you want me to, look up your homework or something, then come to the office hour. That's a different link. And I can open up your homework in WebAssign and look at your PDF and, if you're worried about that, anybody. Thanks for playing. You got plenty to do. You got a special homework and you've got WebAssigns that are going to be due on Sunday. So have a good night.
Thank you.
You too.
Thank you. You have a good night too.